All right, everyone. All right. It's 1:30. I think now's a great time to start. So hello, and welcome. It's good to see everyone's smiling faces again. We've got a test on Monday. How's everyone feeling for it? Feeling good? Not so good? Well, I'm sad to see the thumbs down at first. That's such a shame. Looks a bit more sparse today as well. It's like we almost didn't have a test on Monday. But nonetheless, we'll take a look together. All right, I'm going to start off by showing something that I meant to show you guys at the end of last class. I'll wait for everyone to everyone pile in. If you have an advanced standard calculator on you, I would highly recommend pulling it out and following along with me. I'm going to show you something that might help in a pinch for your test, okay? This is really, really, really important. All right, everyone. All right. Let's take a look. We've got lots of stuff to cover today. We'll do this really, really quick. So, hey, how's it going? So we've got our master standard calculators. I'm not sure if you know this or not, but did you know that your math calculator can actually calculate derivatives and integrals for you? So I'm going to show you that right now. Unfortunately, it works only at a point, but let's try it out, okay? So you see this integral button right here? Actually, in the top left, what we'll do is we'll start with the derivative. So we're going to click Shift, and then we're going to click the derivative sign right here. You'll see a dvx. Now let's say we want to take the derivative of x squared at, let's say, x is equal to 5. So the derivative of x squared at x is equal to 5, we know that should be what? 10, right? We'll move the power down. 2 times 5 is 10, right? So do derivative of x squared, comma, at x is equal to 5. If we enter that in, that gives us 10. Now let's say we have a definite integral over a region. So we'll do the same thing with another function here. We're integrating 2x on the interval, let's say, I don't know, 0 to 5 again. So this definite integral will move the power back up. This will give us x squared at 5. This should give us 25. And it gives us 25. All right, so make sure to keep this in mind. If you're in a pinch on your midterm, your calculator can actually calculate derivatives and integrals for you. All right. Thank you for the little clap there. So with that out of the way, we're going to transition over to our test material for today. What I'd like to do is I'd like to go over some of the questions from the test. I believe it should be around the same amount of time as last time. So I guess this week we're going to do the same thing we did at last test review. We'll do different questions for this tutorial and the next tutorial. So if you want to stick around for both, you can see more different questions, I guess, for the review. And we'll try and get it done. We'll try and get it done in the amount of time we have. So, I've also took away the multiple choice answers. So we'll see if we can try a good test taking strategy might be to try and see if you can get the answer without needing the multiple choice and then referring back to it. So let's give it a try. So our question 1 says we're going to consider the function f. All right. All right, everyone. Okay. All right, guys, we've got lots of stuff to cover today, lots of test material. If you want to have a conversation, just step out into the hall and then you can come back in when you're ready to join us. Thanks. I'm really sorry to do this, but we got lots of stuff to cover today. All right, so we're going to consider the function f whose derivative is shown in the graph below. So here we have y is equal to f prime of x, and it asks us how many inflection points that I guess the graph of f has. Before we start this kind of problem, what does it mean for us to have an inflection point? What is an inflection point? Let's see. Yeah, go for it. Yes, so it's a change in the concavity of the graph. And usually this happens when f double prime of x is equal to 0, right? So let's see. Let's see if we can check this here on this graph. So if we're given f prime of x, what we want to do is to get f double prime of x, we're going to take a look at the derivative of f prime being equal to 0. So really we're just going to check when this function has horizontal tangents here. So here at this point we would have f double prime is equal to 0. Same thing here, 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 and here. So we have 5 points here where our f double prime is equal to 0. Hence, f should have 5 inflection points. So f should have 5 inflection points. Okay, does that make sense to everyone? Awesome. We're going to quickly move along. These questions should be slightly easier difficulty than the ones we cover in tutorial, but perhaps we'll be able to get through them a bit faster then. We have f of x, which is equal to the function x over 4 plus x squared, and it asks us on which intervals is x increasing. To check whether our function is increasing or not, we're going to want to look at the first derivative, so the rate of change of that function. So we'll differentiate here. We'll use our quotient rule. So that's going to be the d dx of our numerator times our denominator. We'll subtract the d dx of our denominator times our numerator, and we'll divide by our denominator squared. Squared here. Okay, so this is going to give us, we'll have 1 times 4 plus x squared minus, when we take this derivative here, we'll have 2x times x over 4 plus x squared squared. Now we want this whole thing, we want f prime of x to be bigger than 0, for it to be increasing. So we're going to check the places where this whole function is bigger than 0. We know that the denominator is bigger than 0 already because it's the square of something else. So we can ignore the denominator for now. So this part is always bigger than 0, so we choose to ignore it. So we'll consider this function. We'll consider 4 plus x squared minus 2x squared, which is equal to 4 minus x squared. We can factor that as a difference of squares. So we'll get 2 minus x, 2 plus x. And we want this to be bigger than 0. So let's take a look at our graph. We'll think back to our quadratics here. We'll have a root at 2 and at negative 2. And this is going to open downwards. So it's bigger than 0 on this open interval from negative 2 to 2. So x is on the open interval negative 2 to 2. Okay, everyone happy with that one? All right, let's keep swiftly moving along. Please feel free to interrupt me if you have any questions. So we'll take a look at f prime of x is given by this rational function here. We have f prime of x is going to be equal to x squared plus the root of x all divided by x. I know we've learned a lot of fancy integration techniques, but like for example, u substitution, which will be on the test. But just from looking at it, I'm not sure if I can find a great u substitution for this question. Does anyone have any suggestions for how? Oh yes, go for it.
So if you expand out the top part, then you'll see it turns. Expand out the top part, then you'll see that's 4 plus x squared minus 2x times x. So that's x squared minus 2x.
Expand out the top part?
If you like that, expand out the top part, then you end up getting 4 minus x squared, right?
You're saying this whole thing is 4 minus x squared?
No, the last question, sorry. The next question.
Oh, yeah. Sorry, we've already... did you have any questions about the last one? Sorry, did I move too quickly through the last one? Someone in the back had an idea. Do you have a question? Visit that row, maybe not. Okay, that's okay. Yeah. try breaking up the integral. So for anyone who's in linear algebra, one way to think about this is integration and differentiation are actually linear operations. If you don't know what that means, don't worry about it. But basically, we'll check that f prime of x here, that's going to be equal to x squared over x plus root x over x. If we divide that through, that'll give us x plus, now root x over x, that's the same thing as x to the 1/2 minus 1, so it'll be x to the negative 1/2. So now if we want to find f of something, let's take the integral. We know from our fundamental theorem of calculus that the derivative and the integral are reverse operations. So we'll try it. We'll take the integral of our f prime of x dx here. That'll be the integral of x plus x to the negative 1/2 dx. We'll use our reverse power rule here. So we'll try adding 1 to the power and divide by the new power. So that'll give us x to the 2. We'll divide by 2. And we'll add x to the 1/2, and we'll divide. Now, if we're dividing by negative 1/2, this will give us negative 2, right? So now we have an explicit form of f. This is f of x. Oh, plus c. Don't forget the plus c. Now we have one more piece of information because we need to find out what that value of c is. Why don't we try and find it by,
Can you explain why it's minus 2x to the half?
oh, sorry. No, you're absolutely right. It's a plus. Yeah, it is a plus. Thank you. Thank you for catching that. Oh, I forgot to turn this around, by the way. I normally turn this around for you guys. There you go. Awesome. Okay. Thank you for catching that. So we've got our expression for f of x in terms of c. We'll use our point here that we know that f of 1 is equal to 3. So we have 1/2 times 1 squared plus 2 times 1 to the 1/2 plus c is equal to 3. So let's try and solve for c here. We'll get that c is equal to 3 minus 1/2 minus 2. So c is 1/2, if I did that correctly. So then from here, if we have f of x is going to be equal to, f of x is equal to 1/2 x squared plus 2x to the 1/2 plus 1/2. Then we should have that f of 4 is equal to 1/2 times 4 squared plus 2 times 4 to the 1/2 plus 1/2. So this should give us 8 plus 4, so 12 plus 12.5. Or 25 over 2, that's probably the better way to write it. Is that okay with everyone? Moving too slow? Awesome. Let's think back. We're going to go to, here, I'll zoom out a bit just so you can take a look at that. We're going to evaluate the following sum, and we'll use our Gauss's trick to help us. So the question says, okay, we need to evaluate the sum from I is equal to 1 up to 300 of I times I plus 3. We might not know how to do this in the current form, but let's see if we can manipulate it to get it into ways that we can solve it with our Gauss's trick. So let's start by expanding the terms that are in the sum. So we have the sum from I is equal to 1 up to 300 of I squared plus 3i. We know that sums are also linear, so we can turn this into two sums. We'll have the sum from I is equal to 1 up to 300 of I squared plus 3 times the sum from I is equal to 1 up to 300 of I. So we've split up our sum now into stuff we know the formulas to. Now we can think back to our Gauss's trick formulas here. We know that the sum of all the I squareds is given by n times n plus 1 times 2n plus 1 over 6. So this will be n, which is 300, times n plus 1, which is 301, times, now we're going to have 2n plus 1, so that'll be 601 over 6, plus we'll get 3 times, the sum from I is equal to 300 of I. That's going to be given by n times n plus 1 over 2. So that'll be given by 300 times 301 over 2. So you could evaluate this one in your calculator, or you could evaluate that in your head. If you do a bit of mental math, you'll get 9,180,500. Just a bit of mental math. Yes, question over there. I don't know actually. The formula sheet should be on Child's Math. I also put it in the admin page, so take a look. It may or may not be. It is? Okay, good stuff. All right. Everyone happy with that one? All right. We'll keep moving. We'll keep moving swiftly along. So we've got another question here. Number 5 says we're going to let s be equal to the function 1 over 25 e to the 5x minus e to the 2x. And the question asks us to find the integrals on which f is concave up. So let's remind ourselves, what does it mean for a function to be concave up? We should check a function is concave up if its second derivative, so if f double prime is greater than 0. So for this one, we can just check this one just by the definition of concave up. We'll try taking the derivative twice and then check one that's greater than 0. So we'll take f prime of x. We'll use our rules for differentiation here. We'll get 1 over 25 times, now the derivative of e to the something is e to the something, so e to the 5x. But we also need to multiply by 5 because of our chain rule. Same thing happens here. Derivative of e to the 2x is e to the 2x. But we also need to multiply by 2 because of our chain rule. So our f prime of x is 1 over 5 e to the 5x minus 2 e to the 2x. We'll take its second derivative here. Sorry, this is the first derivative. This is the second derivative. We'll take the second derivative here. Same thing is going to happen. We'll have 1 over 5 times 5e to the 5x. And we'll subtract 2 times 2e to the 2x. So our f double prime will be given by e to the 5x minus 4e to the 2x. Okay, cool. So our goal now is to find where f double prime of x is going to be bigger than 0. So we want to find when this expression is greater than or equal to 0. Or sorry, just strictly greater than 0. So we can add and subtract both sides of the equation. So we're going to set e to the 5x minus 4 e to the 2x. Oh, sorry. Actually, you know what? Yeah. E to the 5x is bigger than 4e to the 2x. From here, what we can do is we can take the ln of both sides here. So we'll say ln of e to the 5x is going to be bigger than the ln of 4e to the 2x. Actually, you know what? How do we continue with this one? I'm actually not sure if that will work. You have an idea over there on that side? Let's see. Let's find out. You're saying factor out e to the 2x here? Okay, actually that's much smarter. That's a good idea. We'll have 4e to the 2x. Yeah. We know e to the 2x is always bigger than 0, so we can just consider this term here. So we'll consider e to the 3x minus 4 bigger or equal to 0. Thank you for the suggestion, by the way. We'll have to check that e to the 3x is bigger than positive 4. In that case, we'll be checking that 3x is bigger than the ln of 4. So x is bigger than 1/3 times the ln of 4. Is that okay with everyone? So here what we did was we took the ln of both sides, or we converted from from exponential form to log form. Is that okay with everyone?
Yeah.
All right. Let's remark, this is always positive, so we can ignore it. All right. Keep moving swiftly along. Question 6 here asks us to consider the function f whose graph is shown below. It asks us how many values of c are there that satisfy the conclusion of the mean value theorem for f on the interval from -2 to 4. So before we do this one, let's briefly remind ourselves of what the mean value theorem tells us. So the mean value theorem says, okay, given an interval AB and a function f that's continuous on the closed interval, and it's also differentiable on the open interval, it says that there exists some c on the open interval. Should say on the open interval, with f prime of c equal to f of b minus f of a over b minus a. Let's remind ourselves that this tells us that there exists some point where the instantaneous slope is equal to the average slope on the interval. So let's see if we can solve this one here. So we'll consider the average slope on the interval. So the average slope, we're going to be given by this line right here. So all we're going to do is we're going to try and count the number of points that seem to have this average slope. So we'll take a look here. This slope right here looks to be about the exact same. There will be some point here where the slope will be the same because we're going from 0 up to a larger slope. And then here we're at some large slope and we're going to be going back down to a shallower slope. So here will also be about the same slope. Does that make sense? So there will be about 3 places on this graph. We don't know exactly where they lie, but there will be about 3 places on this graph where the instantaneous slope is equal to the average slope over that interval. So because it asks how many values of c are there are about 3, or not about 3, there are 3 points where the instantaneous slope is equal to the average slope over the interval. Okay, does that make sense? Is everyone happy with that one? Yeah, question. I'm sorry? It probably should be a bit higher. We're being a little bit loosey-goosey because we don't actually need to find the points. We just need to be able to show the number of points that are on this graph that will have that property. So the reason why we're taking a look at from here to here, we'll start with some steep slope. We'll end up with a shallow slope. So there's got to be some point where the instantaneous slope, which is somewhere in the middle, will be equal to the average slope. We see here we're going from a point where we have a very small slope, a very shallow slope, to a very steep slope. So somewhere in the middle it'll match. And then the same thing here. Again, we're going from a steep slope to a shallow slope, so somewhere in the middle it'll match. You can also almost think about the mean value theorem as a little bit of an extension of the intermediate value theorem from the first couple of weeks. If that helps you. We'll press on. Question 7 asks, which of the following statements are always true? I'm going to pause this for a second, okay? I know the multiple choice options will give a slightly reduced number of possibilities, but I'd like us to take a look at some of these, and we're going to vote on them in a sec, because there's one in particular that tricks a lot of people. Okay? Take 30 seconds, digest it for yourself. We're going to vote on a couple of these, okay? All right, let's take a look. Okay, who thinks 1 is true? Let's see some thumbs up for true, thumbs down for false. Okay, lots of thumbs up for 1. What about 2? Thumbs up, thumbs down? Lots of thumbs up for 2 as well, but some thumbs down. What about for 3? 3, no one's voting. Some thumbs down here on the right. Let's see if we can take a look together, okay? I saw a hand up. Do you have an idea for number 1?
Yeah.
Let's see. So for number 1, what do you think? Sorry?
It's true.
Yeah, it's true, but what did you have any ideas as to why?
Yeah, because 0 raised to 0. Which is 0.
Exactly. Sorry, it's...
Yeah.
Okay, cool. So for number 1 here... For number 1 here, we see we have a base in... like we have an exponential function here. Our base is going to get incredibly small. But also, we're taking a higher and higher power of a small number. So we're compounding this small number to get even smaller. This is not an indeterminate form. We can actually just tell that the limit of this is going to be 0. So 1 is just true. We'll take a look at number 2 here. I'm going to try something, okay? I'm going to make a purposeful mistake, but I want you to tell me if you see anything wrong with it, okay? So we have this limit as x approaches a of f of x over g of x. We have the limit of g is going to 0, so we have 1 over a small number. We have 1 divided by a really small number. So shouldn't it be infinity? Should the limit be infinity? Why or why not? Why not? I see some head shaking now. Let's see. Yeah, go for it. You're absolutely right. You're absolutely right. So we have to remember that whenever we approach a number, this could approach from either side. So for example, I'm going to give a counterexample here, okay? Let's suppose we have f of x is equal to just the constant function 1. Then we obviously have the limit as x approaches a for any number of f of x is equal to 1. Let's suppose g of x is equal to x. Then we have the limit as, let's say a is 0. The limit as x approaches 0 of g of x is 0. But if we look at the limit as x approaches a of 1 over x, which is f over g, that limit doesn't exist because they diverge in either direction. So this limit does not exist. So 2 is not true. So 2 is false. Okay, now what about 3? What about 3? Can we think of either an example that might show that it works or a counterexample to this one? Take a look. An idea?
1 raised to infinity is not 1.
I'm sorry?
1 raised to infinity is not 1.
1 raised to infinity is not 1. Well, why is that? Like I'm asking, do you have like an example to show why this wouldn't be true?
It's extremely a big number, right? So when you raise 1 over, when you raise it to 1.
So not necessarily. If I multiply 1 times itself a bunch of times, could that give me 1? It could give me 1, right? Like what if f of x is the constant function 1? What if f of x is the constant function 1? If I take that to infinity, that'll still be 1, right? So what we have to find for number 3 is a counterexample such as, now we've all seen this limit in class. For example, the limit as x goes to infinity of 1 plus 1 over x to the infinity. I mentioned that this is going to be a really, really important example. Because we see, if we look only, oh sorry, this should say to the x. If we look at only the inside here, we have the limit as x approaches infinity of 1 plus 1 over x. That's equal to 1. And we have on this outside here the limit as x approaches infinity of x is equal to infinity. So we've satisfied the first two. This is true, and this is true. But we know that this original limit is equal to e. So is statement 3 true? No, it's not. So that one's not true. So we're hearing some murmuring. And do we have any questions about this? Do we need any clarification about this? Yeah? Okay. We showed this a couple classes ago. Do you want me to go through this limit again? Yes? Okay, we'll go through this limit really quickly again, okay? We'll go through this again. Very luckily, we have the L'Hopital's rule theorem right here to help us. So let's say I wanted to evaluate this limit. The limit as x goes to infinity of 1 plus 1 over x to the power x. We'll remember that any number y has the value e to the ln of y. That's the same thing. So I'm going to take this. This is equal to the limit as x goes to infinity of e to the ln of 1 plus 1 over x to the x. I'm going to bring the power down. So I'll say e to the x ln of 1 plus 1 over x. When you have a number, like it's multiplied by other numbers, remember that we can bring it down twice in a fraction. So for example, we know that for any number z, we have z is equal to 1 divided by 1 over z. That's true. So we can say that this is the limit as x goes to infinity of e to the ln of 1 plus 1 over x divided by 1 over x. I'm also going to push this limit inside the e. We can do this because e is a continuous function. E to the something is continuous. So we have e to the limit of x goes to infinity of ln of 1 plus 1 over x over 1 over x. I heard people are saying they're confused. Let's take it back. We'll go slower again. Do each of these steps make sense so far? What part is confusing so far? Oh, was it someone else? I thought I heard someone say that. Oh yeah. I'm sorry? We're using the fact that e to the ln of something is the same thing as that something on its own. So you see here, in the very first step, we use the fact that we can take e to the ln of that same thing and the limit stays the same. So we're using this logarithmic method to solve this limit, just to kind of help us a little bit. In the back, yeah? Oh no, that was good. Does that make sense? It's the same way sometimes we use logs to help us calculate derivatives. So we took e to the ln of this function, we brought the power down, we pushed the limit inside, and now we have a form that we can use L'Hopital's rule. So let's try applying our L'Hopital's rule here. Because we see that we have this value, that'll approach ln of 1, which is equal to 0. Our denominator will also approach 0. So we'll take the derivative of the numerator and the denominator. That'll give us 1 over 1 plus 1 over x. And we'll have the derivative of 1 over x. Sorry, this is really, really small. We'll have 1 over 1 plus 1 over x. We'll multiply by the derivative of 1 over x. Here we'll have the derivative of 1 over x. I'm actually not going to calculate those because those are actually going to cancel out from each other. So we'll be left with e to the limit as x goes to infinity of 1 over 1 plus 1 over x. This is going to tend towards 1. It's going to tend towards 1. So we'll get e to the 1, which is just e. Are you convinced now that that limit was e? Okay, awesome. Do we have any more questions about the 3 true or false? Oh yeah, Adam.
Did you prove the first two are the ones that are confusing?
The first 2 are the ones that are confusing. We'll take a step back. Is everyone okay if I move back up? So we're asking whether these are true and false. Number 1 is true because if we just take a very small number and we take higher and higher powers of that small number, the whole thing is going to get smaller and smaller and smaller. There's nothing indeterminate about that one. That one's just going to go towards 0. The reason why questions or part 2 is not true is because we could have the whole thing go to positive infinity, or the whole thing could go back down to negative infinity. So it's not necessarily true that that limit is infinity. So for example, we chose a counterexample here. We chose an example where f of x is equal to the constant function 1. We said g of x is equal to x. The question says, okay, in that case, the limit of f over g should be infinity, but we showed that the limit of f over g actually doesn't exist. So that's how we found a counterexample to show that 2 is false. Does that make sense? Still a little rocky? Yeah. What I find is really helpful on these true or false questions, whenever you get something that tells you, oh, is this true or false, you should try and convince yourself, if you think it's true, convince yourself that it's true. Try and find some proof to show that it is. Or, if you think it's false, just try and find one counterexample. So you see how in this case, for number 2, we found one counterexample to prove that that's false? Is that making sense to everyone? Hopefully that should be good. Let's keep pushing forward. And if you still have questions about this one, feel free to come up and ask them after class. So let's take a look at question 8 here. It says, consider the function f whose graph is shown below. And it asks us to draw a graph of the antiderivative. So normally you would get the graphs, but let's try and draw it ourselves. So let's get some coordinate axis planes here. Now we know that the graph that we draw should be, the derivative of the graph should give us this. So if we're drawing an antiderivative, if we're drawing the antiderivative of that, we'll be taking the integral here. And then if we took the derivative of our graph, that should spit back what we originally had. So you notice we have, right here, we have the derivative is equal to 0 here. So since the derivative of that point is equal to 0, we should have a flat line at x is equal to 0 whenever our graph crosses through 0. So somewhere we're going to have a flat line here. We also know the same thing right here. Our derivative function will be 0 at that point, so we should also have a flat line at x is equal to 3 somewhere here. This is x is equal to 3. We know that our area is a rate of change down here. It starts very negative and it gets less and less and less negative over time. So that means we should be starting with a function that starts up here and goes down and down and down towards the origin. If we compare the rate of change of this part of the function that we just drew, we would see that the rate of change of this part right here, this has negative rate of change, so it's going down, and this function is negative right here. Our derivative is negative, so it matches. Okay, now once we cross back over, this function continues to go down. So if the derivative continues going down at a much bigger increase, we should have that our graph continues this way. And then it also has to shallow out, so it can be horizontal at x is equal to 3. If we again compare our rate of change back up to what we had right here, you should see that our function, our antiderivative right here is getting steeper and steeper down, and it matches with our derivative because that's getting more and more negative. Does that make sense so far with what we've drawn? Sort of? So our graph should look something of this form. You'll notice that The reason we drew these lines here is because, remember, when we take the antiderivative of something, by our fundamental theorem, we're going to end up with some constant. That constant could push our graph up or down. So the thing with our antiderivative is that it could actually occur at any y value you wanted. It's also good to remember that taking the derivative of any antiderivative will always give the same derivative back. And because we also have the graph of our answer, it should be, you can again draw this roughly loosey-goosey and then compare it to whatever you had before. Oh, that's why you're, okay. Got you. Okay. Oh, is that okay with everyone what we drew here? Awesome, okay. Seeing some head nods, that's good. We're gonna keep pressing forward here. Question 9 tells us, it says to evaluate the following integral. And it says that the answer is in the form a plus b over 2, or b root 2, where a is rational. It asks, what is the value of b? Let's try and compute this antiderivative here. So what I'm going to do is, because it's kind of hard to compute this antiderivative with this square, let's try and expand out this square and see what we end up getting. So we'll have, this is the integral from 1 to 2 of root x squared plus 2 root x plus 1 dx. This will give us the integral from 1 to 2 of x plus 2x to the 1/2 plus 1 dx. If we perform this integration, this is going to give us, remember, by our reverse power rule, we'll get x squared divided by 2. We'll get x to the 3/2, and we'll need to multiply by 2/3, so we'll get 4/3 plus x. And we're going to evaluate this from 1 to 2. If we evaluate this from 1 to 2, we'll get 1/2 times 2 squared plus 4/3 times 2 to the 3 over 2 plus 2. We'll need to subtract everything with 1s as well, so we'll subtract 1/2 times 1 plus 4/3 times 1 plus 1. You could then put that into your McMaster calculator, or you could, again, do that one in your head, and then we'll end up getting, we'll have a plus, I don't know what the integer will be, but we'll get a plus 8 over 3 root 2. So 8 over 3 will be our answer. Is that okay with everyone? Just a simple computation, yeah. I actually don't know. I would suggest, actually I'm not sure. I'm not sure if your calculator is able to do it with the radical. You might want to just, you might want to just take a look at this term and just see how they add together. I'm not sure. All right, let's press on. Let's press on. All right. So number 10 says a box with an open top is to be constructed from a square piece of cardboard 9 centimeters wide by cutting out a square from each of the 4 corners, bringing up the side. You know, I should have brought in a box to do this. I'm going to try and bring in something for the volume of rotation next week, but I digress. Yeah. Oh, have you not done that in class yet? Yeah. It's all good. That's I think is the hardest part of this course, but. So let's take a quick look at what our box is going to look like. So we have a square piece of cardboard. We're going to cut out each of these corners here, like this. So this is 9 centimeters. And each of these corners will have length and width x that we're cutting out. And what's going to happen is we're going to end up forming this box into this shape like this. This is a terrible drawing. But perhaps that helps. So you see what we did is we took our box and just folded up the sides like that. And what we're going to do is we're going to try and find the largest volume this box can have. Now, you'll notice that with these optimization problems, we're going to have two things. We're going to have a set of constraints, which might be inequalities or they might be equations that we need to follow. And then there's also going to be a function that we need to optimize. So we'll find our constraints first. Or actually, sorry, let's find let's find our constraints first. So we know I have a square piece of cardboard, 9 centimeters wide. We're going to want to take a look at our, actually we might not even need to set up constraints here. In some questions you'll have multiple variables where you'll need to substitute and do other things with our constraints. Here actually we only have one variable. So we won't actually need to do any of that. We're just going to want to optimize this function here. We'll take our volume. Our box is going to have height x and each of its side lengths. So our volume is going to be our base times our height times our length. So we're going to have x times 9 minus 2x times 9 minus 2x. What's going to happen is now we're going to want to try and find the optimal points for this volume here. So let's expand this out. And then what we're going to want to do is check the endpoints and check when our v prime is equal to 0. So we'll get x times, I'm going to expand this out part first. So 81 minus 18x minus 18 again, so minus 36x plus 4x squared. Expand that in, so 81x minus 36x squared plus 4x cubed. So we want to find the maximum. If we were to check the endpoints on this interval, we would actually just get 0 volume. So we might not actually have to do that for this example. But we'll take a look at our v prime, which will be equal to 81 minus 72x plus 12x squared. We're going to want to solve this quadratic. This one might be factorable, but what we're going to do is actually just use our quadratic formula here. So we'll get 72 plus or minus the square root of 72 squared minus 4 times 81 times 12 times 2 times 12. We'll get some positive value for x, and then all you need to do is sub that back into our v of x here, our original formula, and that'll give us the maximum volume we can have. Is everyone okay with that example, or do you want me to actually fully complete the rest of the computation? Or do you want to try and get some more theory? Yeah.
I know it's normally when you do optimization questions, you have to decide whether or not it's actually optimal. Sometimes it can be minimum. Do they often ask that on the exams, or like
You wouldn't have to do that because there would be, it's multiple choice. You would pretty well know if it was a maximum. The minimum volume would actually be 0 if we didn't bend up the corners at all. So it would be pretty obvious for questions like this, but maybe in another example it might be wise to check. Good question. Okay. Everyone's getting pretty antsy. It seems like everyone's ready to leave. Is everyone ready to leave? All right. We'll end it there. We'll end it a couple seconds early. But thank you very much for attending, everyone. Hope the calculator tricks helped you, and best of luck on your test on Monday.